Hydrogen contains 120 megajoules of energy per kilogram, nearly 3 times the gravimetric density of gasoline, and its only byproduct when consumed is water. Yet, despite being the most abundant element in the universe, almost none of it exists as a free gas on Earth. It has to be manufactured. Today, roughly 95% of the hydrogen produced in the United States is consumed on-site, right where it is made. The problem is that hydrogen is extremely light. At standard conditions, it has such a low volumetric density that you would need a container the size of a small house just to hold enough gas to power a passenger vehicle. For decades, the primary strategy to solve this has been to mechanically compress the gas into high-pressure cylinders or freeze it into a liquid. But we are reaching the physical limits of mechanical containment. To distribute hydrogen at a global scale, we have to look past physical pressure and change how we approach energy storage. The current industry standard for vehicles is to squeeze hydrogen gas to a pressure of 700 bar, roughly 10,000 pounds per square inch. Safely holding that pressure requires high-cost Type SOR tanks. These utilize specialized polymer liners wrapped in thick layers of expensive carbon fiber to prevent the tank walls from failing under the outward load. Even with these materials, we face the challenge of embrittlement. Small hydrogen atoms can migrate into the atomic structure of metals, degrading the container from the inside and causing cracks. An alternative to high pressure is cryogenic cooling, which condenses the gas into a dense liquid. However, hydrogen only turns liquid at 20 Kelvin, minus 253 degrees Celsius. The energy required to maintain these extreme temperatures can make liquid storage up to 5 times more expensive than simple compression. You can see the scale of this requirement in the massive white storage tank used to fuel the space shuttle on its launch pad. The flaw in this method is boil-off. As the tank absorbs heat, the liquid expands back into gas, forcing the system to vent fuel into the atmosphere to avoid overpressurization. Treating hydrogen as a physical substance to be compressed or frozen results in significant energy loss, high infrastructure costs, and complex safety management. To move past these physical constraints, researchers are turning to chemical storage as a path toward high-density distribution. The concept relies on molecular carriers, specifically liquid organic hydrogen carriers, and solid-state materials like magnesium hydride. These materials act as chemical sponges, binding with hydrogen atoms to trap them in stable liquids or solid powders at room temperature. This approach moves the storage challenge from mechanical containment to chemical bond management, removing the need for 700-bar tanks or cryogenic freezers. The difficulty lies in extraction. Once hydrogen is locked into these stable chemical bonds, it requires a significant input of heat and energy to break those bonds and release the fuel. Research focuses on designing catalysts to lower that energy requirement, targeting 4 main categories: transition metals, metal oxides, halides, and sulfides. Using carbon materials like nanotubes builds transport networks that shorten the distance hydrogen atoms travel, accelerating release. To find the right atomic structures, scientists use machine learning and density functional theory to screen thousands of potential compositions, providing atomic-level insights into how these bonds break. Refining these nanoscale catalysts is a foundational challenge. Overcoming this hurdle is essential for moving chemical storage toward a viable industrial scale. Optimized high-pressure tanks are an engineering achievement and a necessity for current vehicles, but they are likely a bridging technology. The ultimate goal is to decouple hydrogen from the energy-intensive physics of extreme pressure and cold. In a future state, this would allow us to ship hydrogen in standard liquid tanker trucks or store it in ordinary silos, utilizing the infrastructure we already have for global trade. When these materials are perfected, they will allow for the on-demand release of clean energy at the point of use. A zero-carbon economy requires a massive shift in how we produce and use energy, and one of the most significant levers in that transition is our ability to design the chemical molecules that carry it.